Everything you see around you once fit into a space smaller than an atom. That single, impossible fact is the heart of our cosmic story, a tale written in the faint glow of ancient light and the silent expansion of space itself. We are going to journey through 25 incredible discoveries that reveal how our universe burst into existence and unfolded into the cosmos we know today. We will explore the two pillars of modern cosmology, the Big Bang Theory and the mind-bending concept of cosmic inflation. You will walk away understanding the definitive evidence for our universe's spectacular birth. How did a perfectly smooth beginning give rise to the galaxies and stars? And what mysterious force is now pulling the cosmos apart? By the end, you will know the answers. What part of this cosmic origin story feels most unbelievable to you? The story of our cosmic origin truly began with a persistent hiss. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were calibrating a giant horn antenna in New Jersey, aiming to study our galaxy. But no matter where they pointed their instrument, they detected a faint, unshakable static coming from every direction in the sky. They scrubbed the antenna clean, even evicting a pair of pigeons and their droppings, yet the mysterious noise remained. This annoying background hiss was in fact the oldest light in the universe. It is the cosmic microwave background, the cooled and stretched remnant of the universe's fiery infancy. Think of it as the afterglow of the Big Bang itself, a fossil imprint from a time when the cosmos was a mere 380,000 years old. Before this moment, the universe was so hot and dense that it was an opaque fog of plasma, where light was constantly scattered by free electrons. As the universe expanded and cooled, electrons and protons combined to form the first neutral atoms. Suddenly, light could travel freely for the first time. That first flash of liberated light has been traveling for over 13 billion years, stretched by the expansion of space into the microwave static that Penzias and Wilson accidentally discovered. Its near-perfect uniformity was a revelation. The entire sky, in every direction, glows with almost exactly the same temperature, just a few degrees above absolute zero. This incredible smoothness was the smoking gun that solidified the Big Bang Theory over its main rival, the steady-state model, which could not explain this pervasive, ancient heat. Later satellite missions like COBE, WMAP, and Planck would map this background radiation with stunning precision, revealing a sky painted with the faintest of temperature variations. These tiny fluctuations, seen as splotches of red and blue in the famous all-sky maps, are the seeds of all cosmic structure, the blueprints for every galaxy, star, and planet that would ever form. This discovery transformed cosmology from speculation into a precise science, giving us our first direct look at the newborn universe. That faint afterglow tells us what the universe was like at 380,000 years old, but what about its first few minutes? That early universe was a seething, unimaginably hot nuclear furnace. For a brief, explosive window, the entire cosmos was hot and dense enough to cook up the very first atomic nuclei, a process we call Big Bang nucleosynthesis. In that frantic first 3 minutes, protons and neutrons collided and fused, creating the primordial blueprints for everything to come. This was not the slow, steady fusion of a star, but a violent, universe-wide burst of atomic construction. When the universe expanded and cooled enough, this frantic fusion shut down almost as quickly as it began, freezing the cosmic composition in place. The forensic evidence for this event is written in the oldest stars. When astronomers measure the composition of pristine gas in the far reaches of space, they find a universal recipe: 75% hydrogen and nearly 25% helium, with just a tiny trace of lithium. This ratio is a perfect match for the predictions of Big Bang nucleosynthesis. It is a cosmic fingerprint that no other process can explain. Stars forge heavier elements, but they cannot account for this vast, uniform sea of primordial helium that permeates all of space. This universal abundance is one of the most powerful confirmations of the hot Big Bang, a direct snapshot from the universe's turbulent infancy. That universal fingerprint of hydrogen and helium tells us what happened in the first few minutes, but it was an observation made decades later that truly revealed the universe's dynamic nature. Edwin Hubble, peering through the Great Telescope at Mount Wilson in the 1920s, made a discovery that would forever change our cosmic perspective. He found that the faint, fuzzy nebulae scattered across the sky were not mere clouds of gas within our own Milky Way, but entire island universes, galaxies in their own right, lying at staggering distances. And that was only the beginning. By analyzing the light from these distant galaxies, Hubble noticed something peculiar. Their light was systematically shifted toward the red end of the spectrum. This redshift is the cosmic version of the Doppler effect, the same phenomenon that makes a siren's pitch drop as an ambulance speeds away from you. But instead of sound waves, it is the light waves that are being stretched. This universal redshift meant only one thing: nearly every galaxy is racing away from us. Hubble then uncovered an even more profound pattern, now known as Hubble's law. The farther away a galaxy is, the greater its redshift, and therefore the faster it appears to be receding. A galaxy twice as far away is moving twice as fast. This is not because galaxies are speeding through space like shrapnel from an explosion. The space between them is itself expanding, carrying the galaxies along with it. Picture a loaf of raisin bread baking in an oven. As the dough rises, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others are retreating, and the farther away a raisin is, the faster it seems to move. We are not at the center of this cosmic expansion. Any spot in the universe would see the same thing. This relentless outward flight of galaxies is the most direct evidence we have that the universe was once unimaginably compact. If you could run the film of cosmic history backward, you would see all those galaxies, all that matter and energy, converging to a single, infinitesimal point, the moment of the Big Bang. But that very uniformity of the cosmic background radiation presented cosmologists with a profound mystery. Why does the afterglow look the same in every single direction? This is known as the horizon problem, and it points to a deep flaw in the original Big Bang model. Imagine two people standing at opposite ends of a vast, dark room, so far apart they cannot see or hear each other. If you suddenly turn on the lights and both people are already holding cups of coffee at the exact same temperature, how did that happen? Without any way to communicate, how could they have possibly coordinated that perfect thermal equilibrium? This is precisely the situation we see in the early universe. The cosmic microwave background radiation from one side of the sky is at the same temperature as the radiation from the complete opposite side. According to the standard Big Bang timeline, these two regions were so far apart that light, traveling at the universe's speed limit since the beginning, simply did not have enough time to travel between them. They were outside of each other's cosmic horizons, forever isolated and unable to exchange heat or information. Yet they managed to reach the same temperature to within 1 part in 100,000. It is as if the entire universe, from its very birth, was prearranged to be uniform, a coordinated act without any possible director. This paradox suggested that something crucial was missing from the story, a mechanism that could have connected these distant regions before the light of the cosmic background was ever set free. That perfect uniformity of the cosmic afterglow was not the only puzzle left by the classic Big Bang. Another, even more precise, mystery was waiting in the geometry of space itself. Our universe appears to be flat. This does not mean it is shaped like a sheet of paper, but that the rules of geometry we learned in school, where parallel lines never meet and the angles of a triangle always add up to 180 degrees, hold true on the grandest cosmic scales. This observed flatness, however, presents a profound problem. For the universe to be this flat today, its initial conditions had to be calibrated with an almost impossible precision. Think of trying to balance a pencil perfectly on its sharpened tip. The slightest tremor, the tiniest gust of air, and it topples over. Now imagine that pencil is the entire cosmos, and the balance must be held not for a second but for billions of years. According to the mathematics of the original Big Bang model, the density of the universe at just 1 second after its birth had to be fine-tuned to an astonishing accuracy of 1 part in 10 to the power of 60. To grasp that number, it is like aiming for a target 1 millimeter wide from across the entire observable universe and hitting the bullseye. If the density had been even a hair's breadth greater, the force of gravity would have overcome the expansion, pulling everything back together in a catastrophic big crunch. If the density had been the slightest bit less, the universe would have expanded so rapidly that matter would have flown apart into a cold, thin, and empty void. Stars and galaxies would never have had a chance to form. The fact that we are here in a cosmos rich with structure means the universe was balanced on a razor's edge from the very beginning. This is the flatness problem, a coincidence so staggering that it could not be mere luck. It screamed for a physical mechanism, a reason why our universe had to be born with such perfect, exacting balance. The universe's impossible fine-tuning demanded an answer, and it arrived with one of the most breathtaking ideas in all of science: cosmic inflation. This theory proposes that a tiny fraction of a second after the universe began, it underwent a violent, exponential growth spurt. A region of space trillions of times smaller than a single proton was stretched in an instant to a size larger than our entire observable universe. This was not the steady expansion we see today, but a fantastically rapid inflation of space itself, far faster than the speed of light. This single, brief event provides the elegant solution to both the horizon and flatness problems in one stroke. First, it explains the universal temperature. Before inflation, that tiny seed of the cosmos was small enough for every part of it to be in contact, allowing it to even out its temperature into a perfectly smooth, uniform state. Then inflation blew this smooth region up to a colossal size, creating the vast, uniform cosmos we see in the cosmic microwave background. Those two opposite sides of the sky were once neighbors, close enough to share a cup of coffee before being ripped apart by this incredible expansion. Second, inflation forced the universe to become flat. Think of the surface of a balloon. When it is small, you can clearly see its curved shape. But if you inflate that balloon to the size of the entire Earth, its surface would appear perfectly flat to anyone standing on it. In the same way, the inflationary blast stretched the fabric of space so tremendously that any initial curvature was smoothed into the geometric flatness we observe today. The pencil was not balanced on its tip by a miracle, it was glued in place by the physics of inflation. This theory does not replace the Big Bang, but rather sets the stage for it, creating the perfectly smooth and balanced initial conditions that allowed the classic hot Big Bang story to unfold so successfully. Inflation's explosive growth did more than just smooth and flatten the cosmos. It should have shaken the very foundations of reality. The theory makes a stunning prediction that the violent expansion of space itself would have generated primordial gravitational waves. These are not waves of sound or light, but ripples in the fabric of spacetime, first predicted by Einstein. Picture the universe as a taut rubber sheet. Inflation would have been like striking that sheet with unimaginable force, sending powerful tremors echoing through the newborn cosmos. These ancient ripples would have left a permanent, though incredibly faint, scar on the cosmic microwave background. As the gravitational waves passed through the hot plasma of the early universe, they would have gently tugged on it, imprinting a unique, swirling pattern in the polarization of the light, a specific signature known as B-mode polarization. Finding this swirl is the ultimate goal, the holy grail that would confirm inflation beyond any doubt. the hunt for this signal is one of the most dramatic quests in modern cosmology. Teams of scientists have braved the harsh conditions of the South Pole, using telescopes like BICEP to stare at the pristine sky, searching for that telltale swirl in the cosmic afterglow. The drama reached a fever pitch when one team announced a possible detection, a discovery that sent waves of excitement through the scientific community. But the celebration was short-lived. Further analysis revealed that the signal they saw was likely contaminated by something much closer to home, cosmic dust within our own Milky Way galaxy. This interstellar dust can create a similar swirling pattern, mimicking the very signal they were desperately seeking. That moment of hope followed by sobering reality captures the raw, challenging process of science. The search continues with ever more sensitive experiments, peeling back the veil of dust to listen for the faintest echo of the universe's first and most violent moment. The hunt for gravitational waves is a search for the tremors of cosmic inflation, but the theory also predicts the very seeds of creation. Within that explosive expansion lies the answer to one of the deepest questions: how did a perfectly smooth universe give rise to the intricate cosmic web of galaxies? The answer comes from the most unlikely of places, the ghostly realm of quantum mechanics. According to inflation, the energy field that drove the universe's rapid growth was not perfectly uniform. At the tiniest scales, the quantum world is a seething foam of virtual particles, constantly flickering in and out of existence. These are quantum fluctuations, momentary bubbles of energy that appear from nothing and vanish just as quickly. During the unimaginably brief period of inflation, these microscopic wrinkles in the fabric of reality were caught by the runaway expansion of space and stretched to astronomical proportions. A quantum hiccup smaller than a subatomic particle was suddenly inflated to a size spanning light years. These stretched fluctuations became tiny variations in the density of the universe, regions that were ever so slightly more or less dense than their surroundings. Think of a perfectly smooth balloon before you inflate it. On its microscopic surface, there are tiny, random imperfections. As you blow up the balloon to an immense size, those once invisible wrinkles are magnified into vast mountains and valleys. In the exact same way, inflation took the minuscule quantum jitters and blew them up, imprinting them across the entire cosmos as the blueprints for all structure. These subtle density differences are the gravitational seeds for everything we see. A region with a tiny bit more mass had slightly stronger gravity, slowly pulling in more and more matter from its surroundings over billions of years. The slightly denser patches grew into the first galaxies, stars, and eventually the planets we call home. The emptier regions expanded into the vast cosmic voids we observe today. This means the grand tapestry of the cosmos, with its brilliant galaxies and swirling nebulae, originated from random quantum vibrations in the first split second of time. The largest structures in the universe were born from the smallest possible events, a direct link between the quantum world and the cosmic scale. Those quantum blueprints were not left as mere potential. They grew into the grandest architecture imaginable, a cosmic web spanning the entire observable universe. When we finally developed the technology to map the heavens on an immense scale, this structure was revealed in all its glory. Projects like the Sloan Digital Sky Survey have painstakingly charted the positions of millions of galaxies, creating a three-dimensional map of the cosmos. The result is breathtaking and humbling. Galaxies are not scattered randomly through space like stars in the night sky. Instead, they are organized into a vast, frothy network, a spiderweb of cosmic proportions. Gigantic clusters of galaxies, each containing thousands of island universes, sit at the intersections of thin, winding filaments of dark matter and gas. These filaments stretch across billions of light years, connecting the dense clusters like bridges in an unimaginably large metropolis. And between these brilliant strands lie the cosmic voids, immense, nearly empty regions of space so vast that they dwarf the clusters themselves. This is the large-scale structure of the universe, a pattern that echoes the very first moments of creation. How does this connect back to inflation? The subtle differences in density, those quantum seeds stretched to cosmic size, are the reason this web exists. Gravity acted like a sculptor over billions of years. The slightly denser patches, the peaks in the primordial landscape, pulled in more and more matter. They grew into the galaxy clusters and the luminous filaments. The less dense regions, the valleys, were left behind, evacuating to become the dark, empty voids. When scientists run supercomputer simulations of the universe's evolution, they start with those initial conditions predicted by inflation, a nearly smooth cosmos imprinted with tiny, specific fluctuations. They then let gravity work its magic over 13.8 billion years. The result is a virtual universe whose large-scale structure is a near-perfect match for the maps we create with our telescopes. The ghostly pattern we see in the cosmic microwave background, the oldest light in the universe, aligns precisely with the distribution of galaxies we see today. The blueprint matches the finished building. This is one of the most powerful validations of the entire inflationary paradigm, linking the quantum whisper of the beginning to the majestic cosmic web we inhabit. That cosmic web, a structure born from quantum seeds, seemed to tell a complete story of gravitational growth. But in 1998, astronomers peering into the depths of space uncovered a plot twist that rewrote the ending of our cosmic tale. Two independent teams were studying a special kind of stellar explosion, a Type 1 supernova which acts as a standard candle. These explosions always release the same intrinsic brightness, so by measuring how dim they appear from Earth, astronomers can calculate their precise distance. By looking at supernova in extremely distant galaxies, these teams were effectively looking back in time, measuring the expansion rate of the universe billions of years ago. They expected to see these ancient supernova appearing brighter than standard cosmology predicted, evidence that the universe's expansion was slowing down over time, pulled back by the collective gravity of all matter. The shock came when they saw the opposite. The distant supernova were fainter than anyone had anticipated. This meant they were much farther away than their redshifts indicated. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. The cosmos was accelerating, a discovery so bizarre and unexpected that it earned the teams the Nobel Prize. This was like tossing a ball into the air and watching it not only fail to fall back down but shoot away from you at an ever-increasing speed. Something was overpowering the relentless pull of gravity, a mysterious force we now call dark energy. This invisible agent permeates all of space and exerts a negative pressure, pushing the universe apart. Today, we know dark energy constitutes about 68% of the entire energy budget of the cosmos. It is the dominant component of the universe, yet we have no idea what it actually is. Its discovery was a profound reminder that the universe is far stranger than we ever imagined, presenting a final, monumental mystery that brings our story of cosmic origins full circle. Dark energy may be the dominant force in the cosmos today, but it is not the only invisible player shaping our universe. The full cosmic inventory is a profound shock to our senses. If you could gather all the energy and matter in the universe into a single pie, the slice belonging to everything we can see, every star, every planet, every galaxy, would amount to a mere 5%. The remaining 95% is composed of two mysterious, invisible components, dark matter and dark energy. Dark matter, making up about 27% of the cosmos, reveals itself only through its gravitational pull. In the 1930s, astronomer Fritz Zwicky noticed that galaxies within a massive cluster were moving far too quickly. The visible mass of all those stars was not nearly enough gravity to hold the cluster together. It should have flown apart. Something unseen, a vast halo of dark matter, was providing the extra gravitational glue. decades later, Vera Rubin provided even stronger evidence by studying the rotation of individual galaxies. Stars at the outer edges of spiral galaxies orbit at the same speed as those near the center, defying the laws of gravity as we know them. If only the visible matter were present, those outer stars should be flung away into the void. Instead, they are held in place by the immense, invisible grip of dark matter, a cosmic scaffold that permeates every galaxy. This mysterious substance does not emit, absorb, or reflect any light, which is why we cannot see it. We only witness its ghostly gravitational hand at work, sculpting the cosmos on the grandest scales. Dark energy is an entirely different kind of mystery. While dark matter pulls the universe together through gravity, dark energy pushes it apart. Think of it as a property of empty space itself, a repulsive force that causes the expansion of the universe to accelerate. This means the vast majority of the universe, 95% of it, is made of components we cannot directly perceive. We are like actors on a stage, oblivious to the hidden machinery, the dark matter scaffolding and the dark energy engine that creates the cosmic play unfolding around us. Our entire reality is built upon a foundation we are only just beginning to comprehend. This cosmic timeline, defined by dark energy and dark matter, leads us to a profound question: how old is the universe itself? The answer, 13.8 billion years, is one of the most secure numbers in all of science. We did not arrive at this figure from a single measurement, but from multiple, independent lines of evidence that all converge on the same stunning conclusion. The primary method relies on the universe's expansion. By meticulously measuring the Hubble constant, the rate at which galaxies are receding from us, we can essentially run the cosmic film in reverse. Imagine tracing the paths of all these flying galaxies backward through time, watching as the space between them shrinks. No matter which galaxy's perspective you take, all paths lead back to a single point of origin. The math is straightforward. If you know how fast the universe is expanding now, you can calculate how long it has taken for it to reach its current size from that initial, infinitely dense state. It is like calculating how long a car journey took by knowing the average speed and the total distance traveled. The journey for our universe was 13.8 billion years. A second powerful check comes from the oldest objects we can find, the stars in globular clusters. These are dense, spherical swarms of hundreds of thousands of ancient stars that orbit the halo of our galaxy. Using stellar physics, we can determine the ages of these stars. We know how stars burn their nuclear fuel, and the oldest of these are about 13.5 billion years old. This provides a critical consistency check. The oldest stars are younger than the universe itself. It makes perfect sense. The universe had to exist first before it could form the first stars. If we found stars older than the calculated age of the universe, it would shatter our entire cosmological model. Finally, the cosmic microwave background provides the most precise stopwatch. The subtle patterns in that ancient light allow us to measure the universe's ingredients, dark matter, dark energy, and ordinary matter with incredible accuracy. Plugging these values into our model of cosmic evolution gives us an age of, once again, 13.8 billion years. This convergence is a triumph. Three completely different methods, one looking at the expansion, one at the oldest stars, and one at the primordial afterglow, all point to the same moment of birth. We are not guessing, we are reading a cosmic clock that has been ticking since the very beginning. That perfect flatness of the cosmos is not just a theoretical prediction, it is something we can measure directly in the sky. The universe's geometry is written in the size of the hot and cold spots in the cosmic microwave background, and in the late 1990s, two daring experiments went hunting for this cosmic fingerprint. Scientists launched sophisticated telescopes on high-altitude balloons, one named Boom ran G and the other Maxima, sending them soaring above most of Earth's obscuring atmosphere to stare at the pristine cosmic afterglow. They were looking for a very specific pattern, the angular size of the temperature fluctuations. Think of these spots as the cosmic equivalent of a fingerprint's walls and ridges. Their size holds the key to the shape of the universe. If the universe were positively curved like the surface of a sphere, the light rays from the Big Bang would travel on converging paths, making the spots appear larger to us. If it were negatively curved like a saddle, the light paths would diverge, making the spots seem smaller. The data from Boom, Ran G, and Maxima delivered a stunningly clear answer. The most common spots in the cosmic background were about 1 degree across, the exact size predicted for a perfectly flat universe. It was as if the cosmos had drawn a perfect circle on the sky and said, "Here is my shape." This was the boomerang of cosmic density, a measurement showing the universe's total energy density is balanced on a razor's edge. This critical density is the precise tipping point between two cosmic fates. If there was slightly more matter and energy, gravity would eventually win, pulling the universe back together in a big crunch. If there were slightly less, the expansion would forever dominate, leading to an eternal, cold, and empty big freeze. Our universe is perfectly poised between these two extremes, its geometry flat and its ultimate fate perfectly balanced. This exquisite balance is not a lucky coincidence. It is the direct and beautiful consequence of cosmic inflation, which stretched the primordial cosmos so thin that any initial curvature was ironed out into the flatness we observe today. The universe's first 380,000 years were not a silent prelude but a roaring symphony. We can still hear its faint echo today, not with our ears but in the subtle temperature patterns of the cosmic microwave background. This ancient light is not perfectly smooth. It is a mosaic of slightly hotter and slightly colder spots, a fossilized imprint of sound waves that once thundered through the primordial plasma. In that hot, dense fog, matter and light were locked in a violent dance. Gravity relentlessly pulled atoms and dark matter inward, trying to collapse regions into denser knots. But this inward pull was countered by an immense outward pressure from the intense radiation, the trapped light that pushed everything apart. This created a cosmic tug of war, a continuous cycle of collapse and rebound that sent powerful spherical sound waves pulsing through the universe. Think of a stone dropped into a pond, sending out ripples in all directions. Now imagine that pond is the entire cosmos, and trillions of stones are being dropped at once. These are not gentle water ripples, but pressure waves moving at over half the speed of sound through a searing hot fluid. This chaotic resonance continued for hundreds of thousands of years until the moment of recombination, when atoms formed and the universe became transparent. At that precise instant, the music stopped. The waves were frozen in place, their final crests and troughs permanently etched into the cosmic background as the hot and cold spots we now detect. The most common distance between these spots, the preferred scale of these oscillations, is a cosmic gift to astronomers. It acts as a standard ruler. Just as a 1-foot ruler looks smaller the farther away it is held, this fixed acoustic scale appears as a specific angular size on our sky. By measuring its apparent size with incredible precision, we can triangulate the geometry of the universe and measure distances across cosmic time. This fossilized sound wave is the fundamental scale against which we have calibrated the expansion history of the cosmos, allowing us to weigh its components and confirm the existence of dark energy itself. That cosmic symphony of sound waves was frozen into the background radiation, but a far more dynamic record of cosmic structure is written in the light of the most brilliant beacons in the universe. Quasars are the furious hearts of distant galaxies, powered by supermassive black holes devouring matter and shining with the light of 1 trillion stars. Their incredible brilliance allows them to act as cosmic flashlights, illuminating the vast, dark expanses between galaxies. As this piercing light journeys for billions of years toward our telescopes, it passes through a universe that is far from empty. It traverses a complex web of diffuse gas, primarily neutral hydrogen, which clings to the invisible filaments of dark matter. And this gas leaves a unique fingerprint on the quasar's light, a phenomenon astronomers call the Lyman alpha forest. The signature is a specific absorption line, a dark notch in the spectrum of light that corresponds to the energy a hydrogen atom absorbs when its electron jumps to a higher level. But we do not see just one single notch. Because the universe is expanding, the light from a single, distant quasar passes through countless clouds of hydrogen gas, each one at a different distance and therefore a different redshift. Each cloud imprints its own version of that absorption line, shifted to a different position in the spectrum. The result is breathtaking. Instead of one clean line, the quasar's spectrum is slashed with hundreds, sometimes thousands, of these dark absorption lines, a dense thicket of chemical signatures that astronomers poetically call a forest. This Lyman alpha forest is a direct, three-dimensional core sample of the cosmic web. Each line is like a ring in a tree trunk, marking a specific moment in cosmic history and a specific location in space. By analyzing the intricate pattern of these lines, scientists can reconstruct the precise distribution of matter along that narrow, billion-light-year-long corridor of space. They can map the locations of the vast, diffuse filaments of gas and the immense, empty voids. This incredible data set confirms that the cosmic web is not just a theoretical model. It is a tangible, physical structure, and its intricate, web-like nature aligns perfectly with the predictions born from those quantum seeds stretched by inflation. The forest is a living record of growth, showing us how the faint blueprints of the early universe matured into the grand, luminous architecture we see today. Those frozen sound waves from the dawn of time did not simply vanish. They left a permanent echo, a ghostly imprint that we can still trace in the universe today. This is the discovery of Baryon acoustic oscillations, a cosmic ruler etched into the very distribution of galaxies. The same preferred scale, the most common distance between the hot and cold spots in the cosmic microwave background, is also visible in the way galaxies are spaced across the cosmos. When scientists create massive three-dimensional maps from galaxy surveys, they do not just see a random scatter. They find a faint statistical signal, a subtle overdensity of galaxy pairs separated by a specific characteristic distance. What is that distance? It is the expanded version of the ancient sound horizon, the farthest distance a sound wave could travel in the primordial plasma before the universe became transparent. Think of it like a fossilized bubble. In the early universe, each of those dense knots of matter was surrounded by a spherical shell of material, a ripple pushed outward by the intense pressure of the sound wave. When the music stopped at recombination, that shell was frozen in place, a ring of matter surrounding a central, dense region. Over billions of years, gravity pulled that central overdensity into a magnificent galaxy cluster. But the shell itself also collapsed under its own gravity, forming a vast circular network of smaller galaxies and clusters. So, for every massive cluster of galaxies in the universe, there should be a surrounding ring of galaxies at a very specific distance, a relic of that primordial pressure wave. We cannot see these rings with our eyes in the galaxy maps, just as you cannot see the individual ridges in a fingerprint from a distance. But by statistically analyzing the positions of millions of galaxies, the signal emerges clearly, a preferred scale of about 500 million light-years separating galaxy pairs. This Baryon acoustic oscillation, or BAO scale, is the universe's most reliable standard ruler, because we know its true, original size from the cosmic microwave background. We can measure how much the expansion of the universe has stretched it over time. By looking at galaxy maps from different cosmic eras, from the nearby universe to the distant past, we can watch this ruler stretch. This gives us a direct, powerful way to measure the history of cosmic expansion and to probe the nature of the mysterious dark energy that is causing it to accelerate. Our reality is filled with magnetic pairs. Every bar magnet, from a child's toy to the Earth itself, comes with inseparable north and south poles. But what if you could find a solitary north pole, a magnetic charge all on its own? Grand unified theories which attempt to merge the fundamental forces of nature insist that such particles, called magnetic monopoles, must have been forged in the furnace of the early universe. These exotic relics should be incredibly massive and staggeringly common, a pervasive component of our cosmic environment. Yet, despite decades of searching, not a single confirmed magnetic monopole has ever been found. This glaring absence is not a failure of our theories. It is one of the most compelling arguments for cosmic inflation. In the chaotic moments before inflation, the universe was hot and dense enough to produce these monopoles in vast numbers. They should be everywhere, but then inflation happened. That fantastic burst of expansion would have diluted the primordial soup of monopoles, spreading them so incredibly far apart that the chance of one ever wandering into our observable universe becomes almost zero. The entire cosmos we can see may contain fewer monopoles than the number of fingers on your hand. Their profound silence is a roaring confirmation. The monopole problem is solved not by finding the particle, but by understanding why it is so perfectly, elegantly missing. That cosmic dawn, however, was not an immediate event. For hundreds of millions of years after the Big Bang, the universe was adrift in a silent, featureless sea of neutral hydrogen gas. This was the cosmic dark ages, a time before the first stars, when the cosmos was a vast, unlit void. Then, something incredible happened. The first stars and galaxies ignited, and their brilliant ultraviolet light began to flood the universe. This was not a gentle sunrise, but a violent cosmic revolution. That intense UV radiation was so powerful that it blasted through the neutral hydrogen gas, ripping electrons away from their protons in a process called reionization. Think of it as a great cosmic thaw, where the frozen neutrality of the hydrogen gas was melted away by the searing heat of the first starlight, transforming the universe back into a plasma, a sea of free electrons and protons. This epoch of reionization was the final major transition in the state of the cosmos, and it made the vast expanses between galaxies transparent to ultraviolet light once more. Without this event, the light from the earliest galaxies would be absorbed, hidden from our view. So how do we piece together the story of this ancient dawn? We look for its ghostly footprints in two places. The first is in the light of the most distant quasars. As that brilliant light travels to us, it passes through the leftover hydrogen from the reionization era. If the hydrogen is neutral, it absorbs the light fiercely, creating a vast shadow known as the Gunn-Peterson trough. But by the time we observe quasars from a certain era, that trough is incomplete, telling us that the reionization process must have concluded, leaving the gas transparent. The second clue is etched into the cosmic microwave background itself. When the free electrons from reionization scattered the CMB light one last time, they imprinted a specific, large-scale pattern on its polarization. By measuring this signal, we can pinpoint when this great transition occurred, revealing that the cosmic dawn was a prolonged event, unfolding over several 100 million years as the first stellar fires slowly burned away the primordial fog. That same gravity which sculpted the cosmic web also creates the most perfect darkness in the universe. In April 2019, a global network of telescopes unveiled an image that captivated the world, the first direct visual evidence of a black hole. This was not a photograph of the black hole itself, for no light can escape its central point of singularity. Instead, the Event Horizon Telescope captured the black hole's shadow, a stark, dark silhouette set against the brilliant, swirling glow of superheated gas falling into the abyss. This monumental image focused on the supermassive black hole at the heart of galaxy M87 is a triumph of human ingenuity, but its significance runs far deeper than a spectacular picture. It is a radical test of Einstein's theory of general relativity in the most extreme gravitational environment imaginable. The precise size and shape of that dark shadow match the predictions of general relativity with stunning accuracy. The theory passed this ultimate exam with flying colors. Why does this matter for the story of the Big Bang? Because general relativity is the very foundation upon which our entire modern cosmology is built. It is the mathematical engine that drives the expanding universe model, describing how matter and energy warp space-time to create the force we call gravity. The Big Bang theory, from the initial expansion to the formation of galaxies, rests entirely on the validity of Einstein's equations. If general relativity had failed near a black hole, it would have thrown our entire understanding of cosmic history into question. The fact that it holds true, even at the very edge of reality where gravity is so strong that it traps light itself, gives us profound confidence. It assures us that the same physical laws governing a black hole's shadow also correctly describe the evolution of the entire cosmos from its first fraction of a second to the present day. This confirmation from the most violent places in the universe indirectly validates the models we use to describe the most peaceful, the uniform afterglow of creation itself. Yet, even as our measurements reach astonishing precision, a troubling crack has appeared in our cosmic model. This is the Hubble tension, a puzzle so persistent it threatens to rewrite the rules of the universe. The problem is deceptively simple. We have two primary ways to measure how fast the cosmos is expanding right now, a value known as the Hubble constant. One method looks back to the universe's infancy, using the pristine blueprint of the cosmic microwave background. By analyzing the subtle patterns in that ancient light with satellites like Planck, we can extrapolate forward through 13.8 billion years of cosmic evolution to calculate the expansion rate we should see today. This gives us one very precise number. The other method looks at the modern universe using celestial lighthouses like Cepheid variable stars and Type 1, a supernova in nearby galaxies. We measure their distances and their redshifts directly, painting a picture of the current expansion. This gives us another, equally precise number. The terrifying beauty is that these two numbers do not match. The local, modern measurement suggests the universe is expanding faster by about 10% than the prediction from the early universe. It is as if you calculated how fast a car should be going based on its acceleration out of the factory, but when you clock it on the highway today, it is moving significantly quicker. This is not a small error or a measurement fluke. The discrepancy has only grown with better data. The tension implies that something is missing from our otherwise flawless model of cosmic history. Perhaps dark energy is not constant but evolves over time, growing stronger and pushing the universe apart more fiercely than we thought. Or maybe there is a new, unknown type of neutrino that flooded the early cosmos, subtly changing how it evolved. This is not a crisis for science, but an invitation, a clue that our standard model of cosmology, for all its success, is incomplete. The universe is whispering a secret, and the Hubble tension is our first hint of what we have been missing. This Hubble tension is not the only challenge to our cosmic story. The James Webb Space Telescope, humanity's newest and most powerful eye on the cosmos, is now peering deeper into the past than ever before, and its findings are turning our expectations upside down. Instead of a young universe populated only by small, infant galaxies, JWST is finding brilliant, massive, and fully formed galaxies at astonishingly early times. These cosmic giants existed when the universe was a mere 500 million years old, a toddler by cosmic standards. According to our best models of galaxy formation, which rely on dark matter scaffolding and the slow, gravitational gathering of gas, there simply should not have been enough time for such colossal structures to assemble. It would be like finding a thriving, modern metropolis in the middle of the Stone Age. The light from these galaxies reveals they are not just large, they are mature, filled with stars that have already lived and died, enriching the cosmos with heavy elements far sooner than anyone predicted. This presents a fascinating puzzle for cosmologists. The initial conditions from inflation and dark matter seem correct, yet the growth of structure appears to have happened at a breakneck pace. Perhaps dark matter has properties we have not yet accounted for, allowing it to clump together more efficiently in the early universe. Or maybe the first stars formed with a unique and explosive intensity, building up galaxies in a single, furious burst of creation. Whatever the answer, these brilliant, ancient galaxies are not breaking the Big Bang theory. Instead, they are forcing it to evolve, compelling us to refine our understanding of the intricate dance between dark matter, gas, and light that transformed a smooth, primordial universe into the structured cosmos we call home. These brilliant, ancient galaxies challenge the timeline of cosmic structure, but perhaps the most profound consequence of inflation lies in a possibility that redefines reality itself. The same mechanism that so elegantly solved the horizon and flatness problems may have also created a multiverse. This is not science fiction, but a natural, though speculative, outcome of the mathematics that underpin eternal inflation. The theory suggests that once inflation starts, it may never truly stop. Instead, the repulsive energy field driving the expansion can decay in some regions while continuing to inflate in others. Picture a pot of water coming to a rolling boil. Bubbles form and expand rapidly within the churning water. In this cosmic analogy, each of these bubbles is an entire universe nucleating within the eternally inflating background. Our entire observable cosmos, with its hundreds of billions of galaxies, would be just a single bubble in an infinite, frothing sea of other universes. The truly staggering implication is that each of these bubble universes could have settled into a different vacuum state, a different low-energy configuration. This means the fundamental constants of nature, the strength of gravity, the mass of an electron, the very number of spatial dimensions, could be different in each one. In our universe, these constants seem finely tuned for the emergence of life, a fact that has long puzzled scientists and philosophers, but in a multiverse, this fine-tuning loses its mystery. We simply find ourselves in one of the rare bubbles where the numbers worked out, a cosmic lottery winner in a sea of uninhabitable realities. While this idea is currently beyond the reach of experimental verification, it stands as one of the most profound implications of our cosmic origins, suggesting that our Big Bang may have been just one birth among an infinite number in a meta-cosmos without end. This potential for a multiverse brings us face to face with one of the most haunting questions in all of science. Why do the rules of our universe seem so perfectly tailored for life? The fundamental constants of nature, the fixed numbers that govern the strength of gravity, the power of the nuclear forces, and the mass of an electron, appear to be exquisitely fine-tuned. If any one of these values were different, even by a tiny fraction, the cosmos as we know it would not exist. If the force of gravity were slightly stronger, the universe would have collapsed back on itself in a fiery big crunch long before stars could form. If it were slightly weaker, matter would never have clumped together into galaxies. If the nuclear strong force were a few percent weaker, protons and neutrons could not bond, and the simple nucleus of hydrogen would be impossible, leaving the universe with no elements at all. If the mass of an electron were different, the delicate chemistry that forms planets and biological molecules would simply fail. It is as if the universe knew we were coming, setting its dials with impossible precision to create a stage where stars, planets, and ultimately, observers could arise. This is the puzzle of fine-tuning, a cosmic coincidence that seems to whisper of design. Yet physics offers a different and perhaps even more staggering explanation. This is where the anthropic principle enters the story. It is a simple but powerful idea, stating that the universe must be compatible with the conscious life that observes it, because if it were not, we would not be here to ask the question. On its own, this can feel like a tautology, a mere statement of the obvious, but when paired with the theory of cosmic inflation and its multiverse offspring, it transforms into a powerful explanatory tool. If our Big Bang was just one bubble in an infinite, eternally inflating meta-universe, then every possible combination of physical constants would be realized somewhere in that vast ensemble. Countless bubbles would be stillborn, collapsing instantly or expanding into barren emptiness. Others might have laws of physics so alien we can scarcely imagine them. In this cosmic lottery, we simply live in the one bubble where the numbers came out right. We are not the purpose of the universe, but rather the inevitable product of a universe large enough and varied enough to contain a niche where life becomes possible. This idea does not prove the multiverse exists, but it provides a compelling natural reason for the apparent fine-tuning we observe, turning a miracle into a simple selection effect. We are not at the center of the cosmos, but we are living proof that our particular cosmic neighborhood has the right address for existence. This long-term forecast for the cosmos is both majestic and melancholy. If dark energy continues to dominate as it does today, the fate of our universe is not a dramatic collapse, but a slow, cold whisper into eternity. Astronomers call this the heat death or the big freeze. It is a future where the universe expands forever, accelerating into a state of profound darkness and isolation. The timeline for this is almost beyond comprehension, spanning trillions upon trillions of years. The first major change will be the fading of the cosmic landmarks. Over the next several billion years, the acceleration will carry all but the very closest galaxies beyond our cosmic horizon. Their light, no longer able to cross the ever-widening gulf, will simply fade from view. The night sky, which today is filled with the faint smudges of distant island universes, will become utterly black and empty. Our Milky Way will have long since merged with the Andromeda Galaxy, forming a single, giant elliptical galaxy, but it will be an island in a void with no other landmarks in sight. Then the lights will begin to go out one by one. Over trillions of years, the last generation of stars will exhaust their nuclear fuel. The universe will be littered with the corpses of stars, white dwarfs that cool into black dwarfs, neutron stars, and black holes. With no new stars forming, the cosmos will grow dimmer and colder with each passing eon. Even the most durable structures will not last. Planets will be stripped from their dead stars through gentle gravitational tugs, and eventually, over timescales so vast they defy imagination, galaxies themselves will evaporate as their stars are flung into the void or consumed by the supermassive black holes at their centers. Those black holes are not permanent either. Through a quantum process known as Hawking radiation, they will slowly leak their mass away, eventually vanishing in a final, faint puff of particles. What remains is a universe that is cold, utterly dark, and almost perfectly empty. It will be a thin soup of subatomic particles and photons, so spread out by the relentless expansion that they rarely, if ever, meet. The temperature will approach absolute zero, the point where all motion ceases. This is the ultimate equilibrium, a state of maximum entropy where no energy can be harnessed, no work can be done, and no complex structure can ever form again. From a universe that began in a blaze of light and heat, this is a quiet, cold conclusion. The fiery birth of the cosmos leads to an eternal, frozen silence, a story that begins with a bang and ends with the faintest, coldest whisper. Even the quantum seeds for all cosmic structure carry a hidden signature within them. The simplest models of inflation predict these primordial fluctuations followed a specific statistical pattern known as a Gaussian distribution. This means the variations in density were random but statistically simple, like the height differences in a naturally rolling landscape of hills and valleys. Most hills are of average height, with a few very tall peaks and a few very deep valleys, all arranged in a predictable bell curve fashion. This is what our most detailed maps of the cosmic microwave background have so far confirmed, a universe born from a remarkably simple set of quantum rules. But what if that simplicity is an illusion? The next great frontier in cosmology is the relentless hunt for a deviation from this pattern, a signal known as primordial non-Gaussianity. Finding it would be like discovering that the rolling hills of our cosmic landscape are not natural at all, but are instead arranged with subtle, hidden correlations. Perhaps some valleys are systematically paired with specific peaks, or the shapes of the hills reveal an unexpected interconnectedness. Such a discovery would be a monumental breakthrough, pointing directly towards more complex and exotic models of inflation. It would reveal that the physics of the universe's first instance were far richer than our simplest theories suggest, potentially involving multiple interacting energy fields or entirely new principles of quantum gravity. This search for non-Gaussianity represents the next grand challenge. Future observatories like the Simons Observatory and the planned CMB-S4 experiment are being designed with this precise goal: to stare at the ancient afterglow with unprecedented sensitivity, searching for those faint, statistical whispers that could rewrite our story of cosmic genesis. The entire majestic history of the universe, from the first quantum tremor to the vast cosmic web, awaits the verdict of this final, profound test. From that faint hiss in a New Jersey antenna to the swirling shadows of black holes, we have journeyed across the entire history of the cosmos. These 25 discoveries are not isolated facts, but threads in a single, magnificent tapestry, telling the story of a universe that exploded from a quantum seed into a vast, structured, and accelerating reality. We have decoded the fossilized light of creation, uncovered the invisible scaffolding of dark matter, and felt the repulsive push of dark energy. We have watched as quantum jitters were stretched into galactic superclusters and listened for the echoes of the universe's first sound waves. This narrative is a monumental achievement of human curiosity, a story pieced together by peering through telescopes, by launching satellites into the void, and by scribbling equations on countless blackboards. It is a story that is both coherent and wildly unfinished, a testament to the fact that every answered question unveils a deeper mystery, from the troubling Hubble tension to the breathtakingly ancient galaxies now being revealed. We are the first generation to know this cosmic story with such clarity, and the first to see its lingering puzzles so clearly. So tell us, which part of this incredible journey resonated most deeply with you? Was it the sheer improbability of our fine-tuned existence, or the violent inflation that set it all in motion? Share your most amazing discovery in the comments below, and subscribe to join us as we continue to explore the greatest mysteries of the cosmos.